This is Mr. Holsey of H Squared's Officially Understood Science, and today we're going to be talking about the life cycle of stars. So all stars are going to begin in a nebula, and a nebula is a giant cloud of gas and dust, where stars are formed from the remnants of other stars. In fact, most nebula that we see today in the galaxy and the universe are formed from supernova that occurred long ago. So it's very much a cycle. As older stars die out, new stars take its place, utilizing the materials left over from the old star. And so each generation is going to have new elements because as these stars go through their processes, they are going to create heavier and heavier elements like the ones we see on the periodic table of elements. And so there's actually three populations of stars. We have population 1 stars, which are like our own sun, that have metals in them. We have population 2 stars, which are a bit older than ours. They don't have near as much metals. And we have population 3 stars. Population 3 stars would have been the first stars to form in the universe because they would have been extremely massive and been entirely hydrogen and helium. These stars no longer exist. But needless to say, all of these populations would have began in a stellar nursery like the one you see on your screen. Now this specific formation, this specific nebula, is known as the pillars of creation. And it's massive. In fact, if you see these little red dots right here and right here and right here and right here, those are actually stars. So these nebulas are huge, absolutely huge. Now, as this star begins to form, gravity is going to be in control initially, causing the gases to be pulled together, causing it to spin and contract and compress down on itself. This spinning action is going, along with the different atoms bumping into one another, is going to create heat. Now that heat energy is going to cause light. So let me show you why. So let's imagine that we have a hydrogen atom. Now around that hydrogen atom is a single electron. So since heat is energy, what happens is it supercharges that electron essentially and kicks it out to a higher energy level. Now that's not a stable configuration for this atom. So to go back, it's going to radiate that energy out in the form of a photon, causing this electron to fall back down to its normal energy level. So that photon is a light particle. So this continued heating is going to increase the temperature at the core of this spinning gas. And that's important, the increase in temperature, especially when we're just looking at hydrogen here, hydrogen and helium. Hydrogen is going to be the first gas that's going to burn in a star because hydrogen has a fairly low fusion point. The fusion point for hydrogen is about 15 million degrees, which means that at 15 million degrees, hydrogen atoms will fuse together to form helium atoms. But at 15 million degrees, two helium atoms will not fuse together. That's important, especially in the later life of the star. As it goes through, it's actually going to heat up because the core will shrink and it will cause the fusion of heavier elements. So this 15 million degrees, that's when a star is born. Now notice right here in the video, you see the solar winds blowing away the accretion disk. So that leftover gas will form a series of possibly planets or a binary star. And that's not uncommon, by the way. Our solar system is actually very strange in the universe, or in the galaxy, in that we do not have a companion star. It's very rare. And so scientists believe that there may be a companion star way out and we just don't know it, but as of right now, there's no proof of that. But most stars are binary stars, and a lot of the binary stars are made from a larger star forming, blowing off the extra gas, and that gas cooling down and becoming a star itself. Now, during the process of formation, up to the point where fusion begins, gravity is in control of the star. But once fusion begins, the fusion is going to be pushing against gravity. So fusion is a process in which atomic nuclei collide very fast, and hydrogen fuses or joins into helium. Not to be confused with fission. Fission breaks apart, fusion puts together. This causes the star to glow, like I described. So basically think of this like a very large tug of war. Okay, gravity wants to crush the star at all times, but fusion is pushing outwards. Now, depending on the mass of the star, it will have a different lifetime. But if hydrogen and helium, if gravity is pushing down, the pressure of fusion is pushing back. They're basically in a stalemate for millions to billions of years. And so, as this occurs, the pressure is going to remain the same while it's burning the same element. So while all the time it's burning, hydrogen is going to remain about the same. But over time, this star is going to be burning, but it's going to be losing something. So as a star loses mass during fusion, as energy is released, gravity is going to decrease. And let's think about that. Because mass, I want you to remember, force equals mass times acceleration. Okay? So the force of gravity, if mass decreases, the force will decrease. The force necessary to accelerate it. And so gravity will decrease the amount of gravity. So as mass decreases, so does gravity. So more massive objects obviously have more gravity. Now, when that gravity decreases, so here's my poorly drawn star with my poorly drawn core. The core is pushing outwards, and gravity is pushing inwards. So if gravity decreases, and let's think like, force readings, if gravity decreases, now has less force, then fusion, the pressure of fusion, is going to cause that star to expand. And this is for all stars, high mass stars and low mass stars. And it'll become a red giant. Typically, it can become low mass stars will become just straight up red giants. And high mass stars will become red supergiants. And so this is signaling the later parts of a star's life. And so fusion will win for a little while. Now, why does it become red? Because if we think about our EM spectrum, we have blue, green, yellow, just kind of orange, red. I forgot to do violet. But anyway, we have our little EM spectrum. So if our star starts out right here and converts to a red giant, that means the outside temperature of the surface temperature is dropping. And I mean, it's gotten bigger, shouldn't it get hotter? Well, let's think about it like this. Imagine you had a little portable space heater and you went to warm up a room. Now, your room that you're warming up is the size of a closet. It wouldn't take long for that portable space heater to warm it up. However, if you had the same amount of energy, main amount of fusion in this case, or same amount of that heater, and you went and tried to warm up a classroom like a classroom the size of our lab using just that same amount of heat, you would never get that job done. So essentially, we're expanding the amount of area that we have to heat up using that same amount of fusion. Now, depending on the mass of the star during its lifetime, the death of the star is going to be very different. So let's take a look. So we have two different paths here. We have the low mass stars. These are going to be similar to the sun. And we have our high mass stars. And they have at least 25 times the mass of our sun. And so these stars are going to have two very different endings, but a similar beginning. All stars are going to begin in stellar nebulas, whether they are massive stars or low mass stars. So we're going to start off by taking a look at the low mass stars. So an average star like our sun, as its fuel runs out, as it expands, as fusion wins, because remember here gravity's gone down, okay, fusion wins for a bit, okay, it's going to start running out of fuel. And as it does, fusion will begin to slow down. So when the outward force of fusion is less than the inward force of gravity again, the star will shrink in size, expelling its outer layers and leaving behind what we call a white dwarf. These stars are basically corpses. They are no longer creating fusion. which means they're no longer creating new heat. And so they're just going to be out there radiating their energy until the stars actually will turn black, because they'll eventually just run out of energy and they'll turn black and become the same temperature as space. And so this is the fate of our sun. This is what our star will do. It will expand into a red giant phase, shed its outer layers, becoming a stellar nebula again for new stars to begin forming, and be left behind as a white dwarf that will eventually cool down to the heat of the outside environment of space. And so we're going to take a look now at the high mass. High mass stars are going to have a much more explosive outcome, because high mass stars will go supernova. Stars like the sun don't have enough mass to go supernova. And so these high mass stars will, when they go supernova, they will make a massive explosion, needless to say. And it will, depending on its mass, if it's a super massive star, it can become a black hole. If it's a lower high mass star, it will become a neutron star. So a supernova is an explosion that marks the end of a very massive star's life. When these explode, the exploding star can outshine all the other stars in the galaxy in total for totals of several days, and may leave behind only a crushed core. Now, depending on the mass of those high mass stars during its lifetime, the death of that star will be very different. If that star was a massive star but not too massive, the core will crush under the gravity. Okay, in an instant, it'll crush down, but not as much as an extremely massive star. So neutron stars are the smallest and densest stars, with a radius on average of 10 kilometers, which is smaller than a city. Okay, but it has a mass of twice that of our sun. And so, if you were to try to take a spoonful, a cubic centimeter, full of the materials that make up a neutron star, neutronium, which is an amazing concept in and of itself. Basically, it's a star we believe made of only neutrons. And so the electrons are actually, it's so dense, the electrons are pushed into the protons and it creates neutrons, and it's really kind of crazy. But it's so dense that 1 cubic centimeter of this stuff would weigh 1 billion tons. That's insane. A cubic centimeter, less than a spoon full of material, would weigh 1 billion tons, and something the size of 10 kilometers. These star cores also eject pulsars, these beams that you see, that we can detect here on Earth using scientific equipment. So we do know that these neutron stars exist. Also, these stars can spin upwards of 1,000 times a second. They are incredibly energetic and have extreme magnetic fields. Now, if the star is supermassive, it will form a black hole. Stellar black holes are made when the center of a massive star essentially collapses in on itself. Gravity pushes down so much, and the mass is so insane that the core in a fraction of a second, shrinks down so small that the mass collapses on itself and becomes a baby black hole. The black hole will actually eat the star from the inside, but then basically eject a little bit of material. The star is still there, but it's being eaten from the inside, and the black hole causes it to explode, releasing massive energy, 100 times that of what our star will produce in its lifetime. And so when this happens, when the black hole collapses, is created, it causes the supernova, and this thing just ejects material for a moment in extreme power, sending out gamma ray bursts across the universe at the speed of light. Now, once this black hole is formed, nothing can escape from the black hole, not even light, as if it passes its event horizon. And so nothing can escape here. Now, like I said, our star is not doomed for such a cool fate. But as our star has progressed, you'll notice this negative 30% right there. That's just showing the luminosity of our star as it ages. And so it was about 30% less. Now, as we go, and also it grew a little bit in size, it will grow. As we go, about right here is today, and about right here is where the sun will have grown so luminous that life cannot exist on planet Earth anymore. About right here is where our star will grow so much that it engulfs our planet, and eventually becoming a white dwarf. Well, I hope you've enjoyed our discussion on the life cycle of stars. Make sure to like, share, and subscribe, and hit that bell notification to know when we post new tutorials. As always, this has been Mr. Holsey. Thanks for watching, and have a good one.